All right, so today we're going to start in on Unit 3 of this course. We're going to start by introducing a new functional group here, alcohols. All right, to be clear, an alcohol is an organic molecule that has that OH group on there. All right, and so our functional group we call an alcohol. Okay, to be clear, the actual OH group itself, that oxygen-hydrogen single bond, is what's called a hydroxyl group. All right, and so when we're referring to the molecule as a whole, we call them alcohols. But you will hear this term hydroxyl group, and that's specifically referring to that OH single bond there. All right, so alcohols are probably one of the more famous functional groups outside of the organic chemistry world. All right, and that's mainly because of this 2-carbon alcohol right here, which we call ethanol. All right, and ethanol is something that's been around for quite a while in human history. This is what we consider our drinking alcohol. So alcoholic beverages like wine and beer, they don't contain a whole bunch of alcohols. It's not like a mixture. There's one culprit that you find over and over again, which is this molecule ethanol. Obviously, it interacts with our body. It really kind of gives us mild food poisoning, which has, whatever effects of feeling intoxicated. All right, that's really what it is. It's not really great for you. That's why. But yes, super interesting history of alcohol and kind of how it became so widely used by the human race is because it's a byproduct of what's called fermentation. Okay, if you seal a little bit of sugar into a liquid that has bacteria or yeast in there, they will consume that sugar, and because of the absence of oxygen, they'll produce alcohol as a byproduct. That's kind of more of a biology topic. Interestingly, so why did we start doing this? I mean, alcoholic beverages have been around for forever, okay? Back in the day, beer was not as strong as what beer is today. We've kind of gotten really good at brewing and making these like crazy alcohol, 8% alcohol beers or something. Back in the day, stuff was much, much more mild than that. And the reason why it was so widely used is because finding clean drinking water was very, very difficult. So you could instead brew beer that wasn't going to grow any bacteria in it, and that was kind of your source of drinking water. That was your nutritional source in which you were using to stay hydrated. So yes, these sort of like dilute beers sort of took hold as a way of instead replacing what would have been the absence of clean drinking water. Finding clean water was very difficult to do back in the day. So that's kind of why this, and then of course they discovered, oh wow, we drink enough of it, we feel funny, fantastic, right? So it kind of took on a life of its own for that reason. But when we talk about drinking alcohol, we are very specifically referring to one alcohol molecule. Whereas in organic chemistry, we're talking about a class of molecules. Anything that has that OH group on there, okay? So in our day-to-day life, when we say alcohol, we mean this drinking alcohol. All right, in the lab, alcohols are typically used as good solvents. Okay, and we can say, we can be a little bit more specific, they are considered to be the more polar solvents that we use in our lab. Right, so when you're first introduced to this idea of polarity, all of the world is divided neatly into polar, non-polar, this kind of black and white way of looking at the world, wherein in fact, really we want to think of things as being more on a spectrum from the non-polar end to polar. Our most non-polar solvents would be our alkanes, things that consist only of carbons and hydrogens. Okay, we got to get a few carbons on there or they're not liquids, so they're not solvents. Anyway, our most non-polar solvents are our alkanes. Okay, sitting all the way on the polar end of the spectrum would be water. Water is a very famous polar solvent. Our alcohols are very close to that polar end, but not quite all the way. All right, and exactly where that alcohol is going to fall on this spectrum here is really going to depend on the identity of the alcohol itself. All right, so why would that be? Well, we have this OH group. If we look closely at our functional group, this OH group right here, this is a very polar functional group. It can do what's called hydrogen bonding. But because alcohols are organic molecules, they always have this hydrocarbon tail on the back end here. And so although that OH portion of our molecule is polar, the other end of the molecule is relatively nonpolar. Only carbons and hydrogens over here. Okay? So just how big of an alcohol we're using is going to impact where we fall on our polarity spectrum. All right, so let's take a few and we're going to rank these from nonpolar on one end to polar on the other end. All right, I'm going to put down a few molecules here, and you guys tell me where on this little spectrum it's going to fall. The smallest alcohol we could have with just one carbon. All right, so looking at these structures here, which one do we think would be the least polar, A, B, or C? A, because it's got the longest hydrocarbon tail. And which one's going to be the most polar up here? B, because it's got the smallest hydrocarbon tail, right? So if I'm going to kind of organize these in terms of increasing polarity, all right, A is the most nonpolar, followed by C, followed by B. To be clear, these would still all kind of sit further towards the polar end than something that doesn't have that OH group at all, right? But nonetheless, we can sort of tune just how polar or nonpolar our alcohol is. All right, so let's just make a note. The larger that hydrocarbon tail, the more nonpolar the alcohol. Cool, and the other place that you see alcohols, not so much in the chemistry world, but in the medical world, because they tend to be liquids and they kill bacteria, they are often used as disinfectants as well. So like your hand sanitizer that you use has alcohol in them. The alcohol just sort of interacts with the bacteria, kills the bacteria, done and done, okay? So that's kind of the other place that you see alcohols outside of chemistry. All right, so we got a new functional group. The first thing we're going to do is learn how to name it. All right, we got our same step-by-step process here. Let's put down an example. All right, step one is we're going to find and name that parent chain. That's our longest continuous set of carbons. All right, but just like before, we have to make sure that they contain, that parent chain contains our functional group. Okay, so when I'm finding my longest continuous set of carbons in my alcohol, I know this carbon right here has to be involved in that parent chain, right? It's got to contain that OH functional group. So then these 1, 2, 3, 4 carbons would be my parent chain. For 4 carbons, we use what prefix? Bute, all right? And now that we got a new functional group, we're going to need a new suffix. For alcohols, we use that OL ending. All right, step 2, we're going to find and name any substituents. We don't have anything to add to this here. Everything's the same. Now we got to number our parent chain. Okay. Just like before, we want our lowest numbers in our name possible. All right, so number our parent chain. So we have the lowest numbers in our final name. All right, I feel like it's kind of been a minute since we played this game here, okay? But when we get our parent chain, we can always number it in one of 2 directions. We can go from left to right, or we can go from right to left. All right, so which one of these two numbering schemes am I going to pick for this alcohol? Red or blue? Red. I want that OH group to be on the lowest possible number.
It didn't start at the OH?
It did. Oh, you don't, only the carbons get numbers. The oxygen does not get a number. Okay, so then we need to assemble our name. All right, and just like always, we're going to have our locant. Let's just do an example here. So this thing here, if we put it all together, this would be 1, because that OH group is on carbon 1. Bute, because there's 4 carbons. Enol. Okay? So let's pick this apart real quick. That 1 is the location of that OH group, what we call a locant, if we're trying to be fancy. The bute is because we had 4 carbons. All right, we said that alcohols get that OL ending. So what about the AN in this name? It's not just butol, but butanol. That's because this molecule here has all single bonds. Okay, and that's kind of going to be the case with every alcohol that we look at. I'll give you kind of an example. All right, if instead there was a double bond in there, this wouldn't be a butanol, but a butenol. But honestly, it gets a little bit more complicated than that, and we're not going to deal with that in this course. Okay, so just note that if there were double bonds in there, you would not use AN but EN, but again, that's kind of a special case that we're not going to deal with here. All right, so 1-butanol is how we would name this molecule here. All right, we've just because I guess I've been lazy, I've been doing all alcohols where it's on a terminal carbon, but that doesn't have to be the case. I have to build into the name that this is 1-butanol, because if I picked up that OH group and moved it, I could have 2-butanol, right? So you don't have to have that OH group sitting at the end of the molecule. That's why we have to build the location into the name. All right, so before we move on here, everybody take a second. See if you can't name the following alcohols for me. right, so if we find our parent chain, we got these 3 carbons here. We're going to number our parent chains such that the lowest number is where that OH group was. We want the lowest number in our name. So we got 3 carbons in this example. My alcohol group is on carbon 1, so 1 prop. I need the AN in there because there's all single bonds, so 1 propanol. Okay. In our next example here, we have 1, 2, 3, 4, 5 carbons in our parent chain. I can number my parent chain 2 ways. 1, 2, 3, 4, 5. Or 1, 2, 3, 4, 5. Which one am I going to pick, red or blue? Red. So my lowest number, the 2 for that OH group. So now this isn't on carbon 1, but on carbon 2, I have 5 carbons, so 2 pentanol. Cool. All right, so then just some sort of slight complications here. Let's take another example. We're going to throw a halogen in there as well. All right, we're going to find our parent chain just like we normally do. 1, 2, 3, 4. But importantly, when we number our parent chain, this is what we saw the first time we were introduced to our first functional group, alkenes. We're going to number our parent... My bad. We're going to number our dramatic effect. We're going to number our parent chain in such a way that we prioritize that functional group. All right. So when we number our parent chain here, again, we can go 1 of 2 ways. 1, 2, 3, 4, or 1, 2, 3, 4. But we're going to prioritize that OH group, meaning I don't care about the chlorine at all. I'm not going to pay attention to the chlorine when I'm picking my number scheme. I'm only going to pay attention to what gives that functional group, that OH group, the lowest possible number. So in this case here, I don't care that the red numbering scheme keeps my chlorine at carbon 1. I only care about my OH group being on the lowest number. Okay, so everybody take a second. See if you can't remember how we put together our names here. If we got both a substituent and a functional group in there. In the world of nomenclature, there's kind of like this order of importance. And these functional groups are considered to be the most important. The functional group is what we call a suffix. It's in the back half of the name. The other thing, this chloro group here, in the world of nomenclature is considered a substituent. And this goes at the beginning of the name. Let's just say functional group, end of the name. Substituents go at the beginning. So if I'm putting this together here, I'm going to have to list all of my substituents for chloro. That's the only one. Now I get to my 2-butanol. my substituents at the beginning of my name. I got how many carbons and that they're all single bonds. And then I have that OL ending to indicate that this is an alcohol functional group. All right, so it's been a minute, but we saw this with our alkenes as well. The first time we introduced a functional group, we said, all right, when we number that parent chain, we're going to have to prioritize our functional group. That's what we're going to pay attention to when we number. So let's just kind of make a note. We made some rules here. We want our lowest number in the name, but we're also going to prioritize that functional group. When we assemble our name, we put our substituents first. We can just remind ourselves that they're supposed to go in alphabetical order. All right, then we got our parent chain. So we'll say 1, and then that functional group ending. All right, so when we name our alcohols, we got to find our parent chain, our longest continuous set of carbons that contains that hydroxyl group. We're going to use this new ending, this new suffix OL to indicate that we have that alcohol functional group. We're going to find our name, our substituents, just like how we learned how to do before. I don't know, it's been a minute. If we want to just kind of have in our notes here, our common substituents are either alkyl groups, they have that YL ending. So for example, a methyl group, and our halogens see if you can't remember what we call our halogens here. We just did one of them. That was our chloro group. How do we name the other ones? So F would be fluoro and not flowero, but fluoro. Super common spelling mistake. Bromine is the bromo group, and iodine is the iodo group. So of course we covered these when we talked about alkyl halides, but nonetheless, we can kind of have them in our notes. Again, it's kind of been a minute. The halogens and those alkyl groups, they're not considered to be special. They're not considered functional groups. They're instead thrown in this category of substituents, which again means that they're going to be in the front half of the name, not the back half of the name. Cool? All right, let's just do a few more examples before we move on here. right, so each one of these examples illustrates one of the more kind of complex rules of our alcohol nomenclature, really of any nomenclature. So first of all, how many carbons are in the parent chain of this molecule here? Cool, so there is a longest continuous set of carbons that is 6 carbons long, but you have to include the functional group as part of your parent chain. So I can't start counting over here. I have to include these, so my parent chain only has 5 carbons. All right, so then what would this 2-carbon group over here be considered?
Ethyl.
An ethyl group. So it's now off of my parent chain. It is an ethyl substituent. And I'm going to number this thing such that I get the lowest number in the name, but I'm really going to focus on that OH group. Okay. When I put this together, my substituents, they go out front. So this is 2-ethyl. And then my 1-pentanol. All right, so again, we want to just use this example to remind ourselves that our parent chain must contain that functional group. Okay? Bless her. Bless her. All right, so now we're going to find our longest continuous set of carbons. I know it's got to contain this guy here because that's where my functional group is. So 1, 2, 3, 4, 5, 6, 7. Okay. We can number this one of 2 ways, left to right or right to left. Okay, and which one am I going to pick? Red or blue? I really like red today. All right. Because all I'm doing is comparing the location of that functional group. Right? I want the lowest number for that functional group. So that's why I'm going to pick the red. So then these are both considered substituents in my name. We have a bromo group and a chloro group. All right. I need to put them both in my name, even though they're both located on that same carbon. Carbon 6, we're going to put them in our name, and since we have multiple, we need to arrange them in alphabetical order. So what's going to go first in my name, the bromo or the chloro? The bromo. So this would be 6 bromo, 6 chloro. Now we get to our alcohol 3, and there's 7 carbons, heptanol. All right, so again, we're going to use this example here to illustrate 2 important points. One, we prioritize the OH in our numbering. All right, but also in our name, our substituents go in alphabetical order. You can also just note, I had to put the 6 in there twice, right? In this example, they were located on the same carbon, but that's not always the case. There's also 6 bromo, 7 chloro, right? So you got to indicate the location of both of those substituents, even if they're on the same carbon. All right, how many carbons do we have in our parent chain on this one? 5. So now I got these 2 branch points here. So I have these 2 things sticking off of my parent chain. So these would be substituents or 2 methyl groups. Okay, again, I'm going to number my parent chain, but I only care about the location of that OH group. Okay, and now I have two substituents that are identical. So what am I going to say in my name? Not just methyl, but dimethyl. Awesome, okay. And again, I still got to put the location of both of those. So this would be 3,4-dimethyl. What is it? 2-pentanol. All right, so we haven't reminded ourselves of this. We have to use those prefixes. Di, tri, tetra. When we have multiple identical substituents. All right. Cool. So then our last example here, our alcohol. My parent chain is going to be this ring here. And so what's the name of that parent chain? Cyclopent, right? So you got to put the cyclo in front of that since it's a ring. Cyclopentanol. And if I number my ring, that OH group is going to be on carbon 1. So do I say 1 cyclopentanol? No, because if I pick it up and move it, that's still going to be carbon 1. So remember, for these rings that only have one thing on them, we omit that locant. So let's just say no number. 4 rings with one group. If there's more than one, all of a sudden we have to indicate how far apart they are, so we put in our numbers, but not if there's just one. Cool, so we spent a lot of time on nomenclature at the beginning of the course. We also talked about nomenclature last unit, but it was for those benzene derivatives, so it was a little bit different of a logic that we were applying, right? So let's just remember those original rules that we laid out. We always have the same sort of basic structure in terms of how we go about it. We find our parent chain, we find anything sticking off of that parent chain, our substituents, then we number our parent chain, and then finally assemble everything together. We just kind of added some more details to each one of those steps as we've gone along in this course. The big one here, and kind of actually the only new one, although it's been a while since we reminded ourselves of all of them, but the big new one here is that we have a new functional group and thus a new suffix to describe that functional group. Cool. All right. Now we're going to talk about reactions. Okay. This particular reaction, we'll sort of introduce it here and then we'll continue with it next class. But this is kind of a big reaction in the world of organic chemistry, what are called Grignard reactions. It is spelled Grignard, but how I have always heard it pronounced is Grignard. I mean, just fun fact. Always in chemistry, you read a lot of stuff and you just pick one way to pronounce it and you stick with it. All right, might be wrong, might be right. Just go for it. Okay. Anyways, yeah. So Grignard reactions. These are ways to prepare alcohols. From either aldehydes or ketones. All right, but they kind of serve an even more important function, which is kind of rare in organic chemistry. Not rare, but we do have kind of fewer reactions that do this than you would think, is that this is a way to create a new carbon-carbon bond. All All right, up until now we've discussed a lot of reactions, addition reactions, substitution reactions, where you're kind of swapping out functional groups or adding something onto a molecule, but only a small subset. In fact, only those Friedel-Crafts reactions actually created new carbon-carbon bonds. So creating a new carbon-carbon bond is kind of not the easiest thing to do from a chemistry standpoint, so we always just kind of want to make note when we have a reaction that we're learning that creates new carbon-carbon bonds, okay? Because of this, what it means is that your reactant that you start out with, you're going to have more carbons on the product side, right? You're growing your molecule, so it's going to look bigger and uglier and scarier than what you started out with, which means that we have a very important strategy we're going to need to remind ourselves of, which is to count our carbons. All right? Anytime you're growing your molecule, keeping track of how many carbons you should have is really, really important. So just remember when we're doing our Grignard reactions to count your carbons on your reactants and product side, make sure you got the correct amount. Okay, cool. So the Grignard reactions all focus around what's called a Grignard reagent. Which is an example of, and actually kind of the only one we're going to study in this course, but there are a few other out there, what's called an organometallic compound. All right, well, let's pick this word apart real quick. What do we think the organo stands for in this word?
Organic.
Organic. Which of course means all carbons and hydrogens, or at least contains carbons and hydrogens. And what do we think the word metallic means? It's a metal. And so these compounds are going to be these really weird organic compounds. Up until now, every organic compound we've seen has only had non-metal elements in it. Right? The things that live on the right-hand side of the periodic table. These organometallic compounds, they have a metal incorporated into them as well, which we're going to see why that makes a big deal here. All right, so it turns out that if you take an alkyl halide, an alkyl bromide in particular, or at least this works the best, you use an alkyl bromide, and you add in some magnesium shavings, right? Magnesium is just a metal. If you took a sample of magnesium shavings, it literally looks like just ground up chunks of metal. And you throw that in there with your alkyl halide, that magnesium kind of magically works its way between that halogen and that carbon. All right, and so everybody's organic chemistry brain should have just exploded because we have a covalent bond to a metal here, something that we've never seen before, and that is what makes these organometallic compounds very weird. We have a covalent bond. Between carbon and our magnesium metal. And you're like, wait a minute, in general chemistry, we learned that you only have covalent bonds between nonmetals. Yeah, we lied to you a little bit, all right? This is an example of some complicated compound we just haven't seen before. Very rare do these occur. They're not like all over the place, but there are examples of these organometallic compounds that have a covalent bond between carbon and some metal. And this is what we call our Grignard reagent. This is what is used in these Grignard reactions. All right, what makes these reagents so special, I mean, first of all, they're kind of weird, they exist, right? They also work remarkably well. If you did an organic chemistry lab, you would no doubt do one of these reactions because they just work very well. They're very efficient, right? You don't have any pain in the butt set up to worry about or anything like that. The other thing is that there's like no restrictions on what your alkyl halide is that you use. You can start out with anything with a bromine on it and add in magnesium and you will have a Grignard reagent. So there's just a lot of flexibility and great efficiency with these types of reactions, which is why they kind of play an outsized role in like introductory organic chemistry. All right, and last thing, we're going to take this Grignard reagent and we're going to zoom in on it real quick. All right. In the world of nonmetals, carbon is not considered to be very electronegative, right? It's the furthest of the nonmetals away from fluorine. It's considered not very electronegative at all compared to oxygen and nitrogen and the halogens and all the other nonmetals of the world. But compared to the metals, it is still extremely electronegative. So in this compound, when I look at this here, I'm seeing this carbon atom right here glowing red hot with electron density, right? It has managed to pull all the electron density away from that magnesium because magnesium is a metal and metals don't hold on to their electrons very tightly. So we use these certain symbols you might remember from general chemistry. This means that our carbon atom has a partial negative charge. And my magnesium ion, or rather not ion, my magnesium atom here has a partial positive charge. All right, so our Grignard reagents. These are carbon nucleophiles. Remember, nucleophiles are electron-rich species. In our Grignard reagent, our carbon has stolen all the electron density away from that magnesium. It's got a ton of electron density on it. So it is a nucleophile, and it's a carbon atom. So it's what we call a carbon nucleophile. All right, so let's take a look at one of our Grignard reactions. We're going to need to start with an aldehyde or ketone. All right, as a reminder, these are both functional groups that contain these carbonyl bonds, these carbon-oxygen double bonds. And we're going to react this thing with our Grignard. And what we're going to see is we're going to create a new carbon-carbon bond between our carbon that is bound to that magnesium that has all that electron density and our carbonyl carbon of our aldehyde or ketone. So this is where I'm going to form my new bond. All right, so let's take a look up here. Watch me go through this real quick so I can kind of explain my logic. The first thing I'm going to do is I need to draw all these carbons in here, right? So I'm just going to start by redrawing the carbon chain of that aldehyde that I started out with. 1, 2, 3, 4. So that is my blue carbon on my reactant side. And now we're going to create this new carbon-carbon bond. So here's my new bond that I drew. So then what carbon lives on the other side of that new bond? It has to be that red carbon from my Grignard. All right, because again, we get a new bond between the red carbon in our Grignard, the one that's bound to our magnesium, and our carbonyl carbon. Okay, now importantly, in this reaction, what goes flying off into space, or really just kind of gets lost in our solution, is that magnesium and the bromine. Those are not going to appear in our product at all. So I'm just going to add that second carbon, so I got all my carbons from my products, or from my reactant side. All right, so to be clear, I got one extra carbon. Okay, so then what happens to that carbonyl oxygen? Like I said, this is a way to prepare alcohols. So our carbonyl, our carbon-oxygen double bond, is simply going to become a carbon-oxygen single bond on our product side. Still attached to that same blue carbon, all right, but that's our alcohol product that we get with our new carbon-carbon bond between our Grignard carbon and our carbonyl carbon of our aldehyde or ketone. All right, and then I'm going to go and I'm going to count my carbons, really kind of just color them here so we can see what's what. Starting at this end here, I got 1, 2, 3, 4. That's my 1, 2, 3, 4. I got my new bond to the red carbon on the other side, and I have these 1, 2, 1, 2. So I have all carbons from my reactant side accounted for on my product side. All right, and yes, different from when we were, say, swapping out a chlorine for an OH or something like that, right? We're growing our carbon chain on our molecule. So what we end up on the other side is with something that's a little bit bigger and uglier than what we started with, which is why counting carbons is going to be really important. Okay, let's try to do another one. I'll do it, leave this one up here so we can see by analogy here. See if you can't give me the product of this Grignard reaction between this aldehyde and this Grignard reagent. All right, so I'm looking at this reaction here and I see that MgBr. So I'm like, all right, this is a Grignard reaction where I need to form a new carbon-carbon bond. So I want to identify which carbon in which one of these reagents I'm going to need to join together here. And again, that's going to be the one bound to that magnesium ion, magnesium atom, and that carbonyl carbon, the one at the base of my carbon-oxygen double bond. These two are the ones I need to connect with my new bond. So I'm going to start drawing here. All right, I'm just going to start with that aldehyde, which had 3 carbons. And now that I've drawn that 3rd carbon, that must be my blue one here. So then when I draw my new carbon-carbon bond, which one must be on the other end of that? That red carbon. Okay? Now in this case, that magnesium wasn't sticking out on the end of a molecule, but rather was in the middle. So I got to be good, and I got to draw that that red carbon is bound to 2 other carbons. Boom, boom. Again, I'm not going to worry about my magnesium and my bromine. They're not going to be in my product. But what else do I need to include? That OH group, right? My alcohol group. My carbonyl oxygen, it doesn't go anywhere. It's still there. But it does get reduced from a carbon-oxygen double bond to just a carbon-oxygen single bond, which is, again, why we put this under our preparation of alcohols reaction here. So I start out with a 3-carbon aldehyde and a 3-carbon Grignard, and I get a 6-carbon alcohol as my product. I'm going to make sure, counting carbons, 1, 2, 3. Cool. I got 1, 2, 3. Cool. All right, and again, the carbons that I have my new bond between are that carbonyl carbon and the one that is bound to that magnesium atom. All right, so these have both been examples using aldehydes. If you remember back from when we were identifying functional groups, an aldehyde is a molecule where that carbonyl is on the very end. All right. We can play the exact same game with a ketone, but we're going to get a little bit of an uglier product because that carbonyl carbon is a little bit more crowded. A ketone, remember, is when we have that same carbon-oxygen double bond, but now it's in the middle of a molecule. All right, so again, things are going to be a little bit more crowded, but the name of the game is still the exact same. See if you can't give me the Grignard reaction here between these two. Oh, sorry, that is very low. My bad. All right, so I'm going to start by redrawing my ketone. I get to that third carbon, that's my blue. I still got one more to add on there. So there's my 4 carbons from my ketone. All right. I'm going to have to draw my new carbon-carbon double bond. On the other end of that would be that red carbon from my Grignard. But then also that OH group, because that carbonyl oxygen is still attached. It's just now a carbon-oxygen single bond instead of a carbon-oxygen double bond. All right, so things are a little bit more ugly and crowded. But again, I start out with my 1, 2, 3, 4 carbons from my ketone. I'm again forming this bond between those same carbons that I identified before, the carbon bound to the magnesium and the carbon at the base of that carbon-oxygen double bond. And now I'm going to add on those 2 carbons from my Grignard, 1, 2. So again, we get this alcohol product, but it's got a new carbon-carbon bond. Cool. And so this same game we play with aldehydes. Either aldehydes or ketones will react with those Grignard reagents to form alcohols. And again, the whole thing about these Grignard reactions is that you create a new carbon-carbon bond in the process. Break. We'll pick up with this next class.
Do you know when exam grades?
So that, yeah, I've got notice I can go pick them up, but I have not yet, so I will get to grading them this weekend.